Yeah, I'm Daniel, and I want to talk about compboost, a package for model-based boosting or component-wise boosting. And yeah, the package was written together with Yannick Thomas and Bernd Büschel. And before we dive into a bit of methodology and code, I want you to imagine the following situation. So we are selling beer, we have a small booth at the city center, but since we are very responsible persons and we care about the health of our clients or of our customers, we don't want to sell beer to people who drink too much. So that's some kind of philosophy, right? And so therefore we have collected data to estimate how much a customer will drink. So we have collected 200 observations, and we have the beer consumption in liter per year. We have the gender, the country, the age, the weight, the height. And we have also collected 200 features from app usage. We have collected 200 features from app usage. And one note here, the data are simulated, so this is no real data set. And I have just used the country and the age who affects the beer consumption. Okay, so all other features are noise features. So this could be a first task to select the noise-free features from real features. Good, and with this data we want to answer the following questions. First of all, which of the customer's characteristics or features are important? So if a new customer came to our booth and wants to buy beer, should we say, hey, you're from Germany, you're all drinking too much beer, so we don't sell beer to you? Or is it maybe the age or the height? So this is the first task. And then we also want to know the effect of our important features. So if the age is important, we want to know if we should sell to middle-aged people or older or younger people. Yeah. And finally, we also want to know how well our model behaves on new unseen data, because this is what in machine learning counts, it's generalization and not the performance on the trained data set. Good, and just by asking these three questions, we are very restricted in the model choice, right? We cannot use a linear model here because we have more features than observations. A random forest or gradient boosting with trees is hard to interpret. So, you may have guessed we want to use component-wise boosting here. And first of all, what is component-wise boosting? So it fits into the gradient boosting framework, where we start with a constant model. It's the most easiest model with no features in there, it's just a constant model. And in component-wise boosting, we're using univariate model for each feature or for a subset of the features. So we build a spline around the age, we build a spline about the height and so on, and these are all single base learners. And after we have calculated the first model here, the constant model, we can calculate the error we're doing in predicting the target variable. And now we're looping over all individual models and fit them to the error and choose the model who explains the error the most or the best. And this is added to the trace, and we're doing this over and over again. After adding this base learner here, we calculate the new error, which hopefully improves, and then fitting again the individual base learner, selecting the new learner, and so on and so on. So this is the basic algorithm of component-wise boosting. And this has some nice properties. First of all, we have selected two base learner here, right? The third and the first base learner. So we haven't selected the second base learner. So we have an inherent feature selection. The second thing is, since we are just using univariate models here, in this case, we can fit the model in very, very high feature spaces. So we are not restricted to something like p smaller than n situations or stuff like that. And another very nice property is that we have the trace how the model evolves. So we see here, maybe the first base learner is fitted and the second base learner and so on and so on. And we can see after 300 iteration, we have included 3 features. After 400 iteration, we have maybe already 4 and so on. So this is pretty nice in component-wise boosting that we can jump very easily back and forth and have a look at the model at different iterations. Okay, but now about compboost. And first of all, there is already a very, very good package for model-based boosting called mboost, which has a large number of available base learner and losses, and it is extended to more complex data situations like functional data or the GAM LSS situation. But the problem with mboost is that it gets very slow for large data sets because it's completely written in R and they store too much information in each iteration. And also it's a very complex implementation. It had nested scopes and a mixture of different R class systems, which is very difficult to read. So our idea is to have a package which is completely written in C++ to obtain high performance and full memory control. And we also want to use the class system from C++, because a machine learning algorithm consists of different parts. We have the optimizer, we have the loss function, we have whatever, and we want to exchange these parts and look how the model performs with maybe a different optimizer or another loss function. So that's why we choose the object-oriented style here. And then we expose the C++ classes with the RCPP modules to R. And finally, that's a lot of wrapping, but I hope that's okay. And finally, we provide an R6 interface or R6 API for convenience. Good, and now a small demonstration. We remember the beer data. We want to estimate the beer consumption of our clients, our customers. Good, and first of all, we use another convenience wrapper, which is the BoostSplines function. And this function adds a GUM for each feature. Okay, so each feature now is represented as a GUM with splines. And we specify the data, the beer data, the target variable, the loss. Here we use the absolute loss, not the quadratic loss. And here you can also see that this is a class. It's not a free object or a list or something like that. This here is a class which we pass to the model. Good, we specify the learning rate. We want to train the model 5,000 iterations. The penalty is a spline. This is a parameter for the splines. And this is also very interesting, the OOB, the out-of-bag fraction, which is the test set. So we can, during the fitting process, we evaluate our model on the test set or on the holdout set. And we want to print the trace every 2,500 iteration. Good, and when we start, in the first iteration we have a risk of 24, and the out-of-bag risk is also 24, so there's nothing really happens. But during the fitting process, the risk gets better. So we're minimizing the risk here. And the risk on the training data set is getting very fast, very low. So we're here about 0.5. And on the trained data set, we are not that good, but that's the common behavior in machine learning, that we are not able to generalize that good on new data than on the training data set or training data. Good, and after the fitting process, we can visualize the results by, for instance, having a look at the in-bag and the out-of-bag risk, or the train and the test risk. And here, we see the in-bag risk or the train risk gets lower, and then here, after, 2,500 iteration, it's not getting better. And the test risk is also getting better, but here, after 2,000 iteration, it looks like the model isn't able to learn anything more. But we train the model much longer than these 2,000 iterations. And this is a problem here, because now we're starting to fit against the noise, and we overfit our model. And we can see this here, because as I said, the app usage features are just noise features, so they don't have any relationship to our target variable. But our model says, hey, this feature is very important, you should have a look at it. But it's total crap here to look at this feature. So we want to have a look at our model here at 2,000 iteration, because this looks okay. So we can just call again train 2000. And this is what I also told you, that we can very easily jump back and forth in the iterations. So we don't train the model from scratch, we jump back within maybe, a second, instead of training everything again. And if we now have a look at the feature importance, it looks pretty nice. Here we have the age, and we have these country categories, who are the real driver for our target variable. We can also have a look at the effect of these models. For instance, here for the age, this is how the effect evolves. But the final effect is here at 2,000 iteration or 5,000. There's no huge difference. But here we can see that middle-aged people, or people between 35 and 60, don't drinking that much as older and younger people. So maybe we should just sell to middle, or we shouldn't sell to older and younger Czech people. Okay, perfect. Okay, but I told you we have exported the classes, or we provide an R6 API. And this is what really happens inside the model. We first define our compboost object, and then we add the base learner, which looks pretty, not that pretty here to add everything manually. That's why we provide this wrapper function, but you can also very easily apply over the features or something like that. And what can be done with the R6 interface, which is not possible with the wrapper function, is to add logger and stopper, because we also want to do early stopping. So maybe we want our model to be automatically stop here at 2000 iterations, because the risk doesn't improve that much here. And we can also add logger. In this case, we use a time logger, and we say we want to train the model just 200,000 microseconds, and we want to use this as stopper. So after this 200,000 microseconds, the model breaks, and we have just trained about 3,000 iterations. But we can do the same with the performance logging on the in-bag or the out-of-bag risk, and maybe with any performance measure, with a AUC, with I don't know, whatever. Good. Okay, so this is the R6 interface. This is the functionality. So we have at the moment polynomial base learner, spline base learner, and you can define custom base learner, even with R or with C++, without recompiling the whole package. As loss function, we have a quadratic loss, absolute loss, quantile loss, binomial loss, and so on and so on. Okay, a few words about the performance. The package, we have parallelized the feature selection process, because the base learner can be fitted very easily in parallel. And this gives us a speed up, let's say here with 16 cores, of about 8 or 9, a factor of 8 or 9, which is pretty nice. And we also take advantage of the matrix structures. So we store sparse matrices, we pre-calculate objects or matrices who are reused over and over again, instead computing them every time from scratch. So we try to do the model fitting as fast as possible. And compared to mboost, we're then about 20 times faster, 22 times faster on 16 threads. With just one single thread, we're about 2 times faster, which is also pretty nice. And the memory consumption, as I said, mboost has a very, very high memory load. So for instance, here with 2,000 observations, 20,000 observations and 200 features, mboost uses 1 GB of RAM, and compboost uses just 300 MB, which is also a bit, but it's 3 times less memory usage. Okay, and what's next? So we want to use the package or the algorithm for research. We have a few ideas how we can improve the selection process. For instance, by adding a resampling technique for the selection process. And also we want to have the baseline selection for arbitrary performance measures, because at the moment, or the classic model-based boosting algorithm uses the MSE to select the best base learner, but this may not be the best solution sometimes. And we want to, of course, have smart and faster optimizers, maybe a second-order optimizer. We also want to include greater functionality. Functional data structures are very interesting. Unbiased feature selection is also possible. And we want to do stuff like reducing the memory load by applying binning, so by categorizing numerical features and then do calculate weighted base learner. We want to include the package in the MLR or MLR-free framework, so then you can also do imputation before the fitting and hyperparameter tuning. And we also want to expose the classes to Python. Okay, that's basically it. You can have a look at the slides on my GitHub account. The package is actively developed on GitHub. There's a CRAN version, but it's a very, very unstable version. So I will upload the newest version in the next weeks, I guess. And then it should, yeah, then the stable version is also on CRAN. And yeah, there's a just paper and the project page. Okay, thank you.
Thank you, Daniel. Questions? Yeah.
Yeah, actually, in your graph about the importance of the different variables,
Yeah.
did that come out the way you have designed it in the simulation? Since it is simulated data, you know what's important.
Yeah, sure. In this case, sure, the data are simulated with these two features as important features, and sure, in this case, it's obvious that these are the most important features. But I think it's very interesting to see that it starts to fit against noise features, and we can, yeah, when we do the correct stopping, which is very important here, can differentiate between noise features and the real features. And I think, as I said, we want to include a resampling strategy here to get a more stable feature selection. Okay.
Yeah, thanks. Very impressive work. I wanted to ask a couple of questions. First, in the slide 11,
yeah.
Sorry, slide 10, you showed that the risk stops at around 8 point something, and then slide 12, it's actually 3.8.
Sorry, where?
Yeah, so in this slide.
Yeah.
So I was just wondering what's the reason, and then maybe a second unrelated question. So what would actually have happened if you simply use the usual? So you skip the boosting, would you still get this image? So I think normally if you start simple,
yeah,
that's the question. So what would be the big difference?
Okay, do you mean the big difference, sorry, here?
Yeah, so here I'm actually asking a couple of questions. First on this risk.
Yeah.
Why is it now much lower?
Do you mean the risk or?
Yeah, the risk.
Yeah, the risk. So this is something I don't tell you. I have used a different loss here, the quantile loss, and so.
Yeah, so
yeah, the risk is lower, and here we are stopping at 3,000 iteration, and I think it's not fully trained the model. So we have to let this go for another, I don't know, 3,000 iterations, and then there should be a gap between the train and the test error. And the second question, what was it again?
Say I don't use this.
I
don't use this complex methodology, but I use the regular. You know what
linear
everyone
model.
else is doing. Check the lasso, for example.
Yeah. Yeah, sure. I think you can also use a regularized linear model. And basically gradient boosting or component-wise boosting, if you train this infinity long, you will end up in a regularized linear model or regularized GAM. But the nice thing is, as I said, you can jump between the iterations, and this implies different stages of penalization in the model. Instead of training, I don't know, 100 models for 100 different penalization terms, you just train one model and jump back and forth and have a look how well it behaves. So this is one advantage, but sure, you should do a model selection, or should do something like that.